Hello students, in this video we're going to solve the monocentric model exercise. But in particular we're going to start with the consumer setting, then the producer setting, which in this case is a developer. Then we determined the size of the block in this case, then the optimum size of the land, in other words how big the city must be. Then we'll find the equilibrium. And then we'll do the same things, but now let's suppose that the population grows. So let's set the question. In this exercise, we find the equilibrium of a city under some specific assumptions about land use. We are going to assume that all dwellings must contain exactly 1,500 square feet of floor space, regardless of the location, and apartment complexes must contain exactly 15,000 square feet of floor space per square block of land area. Let's suppose these land restrictions were imposed by a zoning authority. In other words, these will make the dwelling size and building heights not vary with distance to the centers, to the central business district. The distance will be measured in blocks. Now, let's talk about the consumer. Suppose that the income per household is $25,000 per year. If you recall, the utility of the person in this case depends on how much housing they consume, Q, but also on all the other goods bundled in this one item that we'll call bread. So the income per household is $25,000 and we're going to use units of 1,000. Therefore, Y will be equal to 25 and Y will be the income. Let's suppose that the cost parameter of commuting is 0.01. If the person lives 10 blocks from the central business district, then they will spend 0.01 times 10 blocks equals 0.1 per year. And since we're talking about thousands, this means $100. Therefore, the consumer budget constraint is given by how much money spent in C and how much money spent in housing. Housing is given by Q, the quantity, multiplied by the price. Now, in this case, we already know that each apartment is 1,500 square feet. So it's 1,500 square feet times the price. This is equal to the income minus whatever the person spends commuting. Okay, so here we have the same consumer budget constraint, and we just substitute the numbers that we have. Now, solve for what is the price? What is the price in terms of the optimum consumption of C and the distance X? So basically, we just plug in our numbers. We use C as if C was a constant, and then we subtract minus C star from both sides. And that leaves us with 1,500p minus everything else. And then we divide both sides by 1,500. We get that p is equal to 25 minus 0.01x minus c star divided by 1,500. And that's the p in terms of everything else. So that's our first solution. B, the second question they ask, recall that the zoning law says that each developed block must contain 15,000 square feet of floor space. Suppose that annualized cost of the building materials needed to construct this much housing is $90,000. Okay, the profit per square block for the housing developer is equal to $15,000 times P minus 90 minus R, where R is the land rent per square block. Now, in equilibrium, the land rent must adjust so that this profit is zero. Let's set the profit equal to 0 and let's solve for the land rent in terms of P. And then substitute with what we knew P was before. So basically, this is the equilibrium condition, that the rent obtained from these square feet, it's equal to 15,000 P minus 90. Now, we already know that P from solution A was 25 minus 0.01 x minus C star divided by 1,500. So we plug this instead of the P. And when we do that, then we can just realize that 15,000 1000 divided by 1500, it's equal to 10. Therefore, this becomes 10 times 25 minus 0.01x minus c star minus 90. And now we can express R, the land rent per square block, in terms of distance and in terms of C star, in terms of the consumption of the bread of the other good, and in terms of distance to the core. 10 times 25 minus 10 times 0.01 x minus 10x minus 90. And then we just add together all these equal terms, and we get that R is equal to 160 minus 0.1 x minus 10 c squared. So that's the developer function in terms of distance and c. Now we're going to determine, well, what is the size of the block that is more adequate. Each square block contains 15,000 square feet of housing, and each apartment is this size. So if we divide this by this, we know that each square block of the city has 10 homes. Now, this is a circle, right? And the area of the circle is given by r squared times pi. So a city with a radius of 10 bar blocks would accommodate 10 times pi x bar square households, because this is the area of the city in terms of square blocks. Now, if the city has 200,000 households, how big must this radius be so that everyone fits? So we have that this is the radius, and now we basically solve this equation for x. That way we can see how many blocks we need. So by dividing both sides by 10, putting pi below, which is 3.1416, and then squaring, we get something very close to 80. So x bar is 80. The size of the city must be 80 in terms of blocks. For the city to be in equilibrium, housing developers must bid away enough land to house the population. Now suppose C star, the consumption of other goods, it's given by 15.5. And suppose the R in the agricultural sector is equal to 2,000 per square block of land. This means that the R in urban setting must also be equal to 2. Otherwise, they would just go to the agriculture sector. So let's substitute C star into the land rent function and compute the boundary of the city. In other words, how big the city is. And then let's see how many blocks we need for housing the population. So first of all, we go to solution B to remember that R is equal to 160 minus 0.1x minus 10c star. And now we can substitute instead of R the 2 that's coming from the rent per square foot. So we put the 2 here. And now basically and now we know that C is given by 15.5. If we plug 15.5 right here and we solve for x, we get the distance, or how many blocks we have, the size of the city. So here we're solving for x. First, we add 0.1 on both sides. So we get 0.1x equals to 160 minus 155, and then I subtract 2 on both sides, and I get that 0.01x equals 3. If I divide 3 by 0.1, we get that x is equal to 30. Okay, so this is the size of the city. Is this enough? We remember that x was supposed to be 80. To have the radius had to be 80 in order for everyone to fit. So no, x is not enough. We need a bigger city. Okay, so let's adjust C. The consumption will be adjusted until we find a value that leads to the city to have the right radius. Of course, we're assuming here that we cannot change the size of the city. This is what's happening. So let's go ahead and plug the right amount of x that we need, which is 80. In this case, then we have from this equation that 2 is equal to 160 minus 0.1 times 80 minus 10c squared. Now we need to solve for c star. We add 10c on both sides and we get that 10c star, it's equal to 160 minus 0.1 times 80 is 8. And then I subtract 2 from both sides. and that is 150. So C star would be 150 divided by 10, which is 15. So C star must be equal to 15. In other words, the consumption of the other good, the bread, is equal to 15. Okay, so if C star is equal to 15, what's the equilibrium land rent function? What is the rent per square block at the center, where x is equal to 0, and what is the rent per square block in the edge of the city, where x is equal to 80, right? Because this is the amount, 80, that we need to survive. Okay, let's start with that. Then we plot the land rent function, and then we calculate how much the farthest household is spending on commuting. So write down the equation for the equilibrium land rent function. So we have the rent function equals R equals 160 minus 0.1x minus 10 times 15. That is 150. And from here we can just simplify to R equals 10 minus 0.1x. And now we have a function of R, which is the land rent, in terms of distance, which is precisely what we needed. Sometimes the distance is 0 when you are really there in the CBD, but sometimes distance will be 80 when you are the farthest from the CBD. And then there's all these values in the middle. So when you have a distance of 0, your rent is 10, and when you have a distance of 80, your rent is 2. Now we can just plot this. This is a line with a negative slope. It starts in 10, it goes down with a slope of 0.1, so it'll touch the x-axis in 100, and then we have here that the rent at 2 will give us the equilibrium because this is the rent outside of the city. So how much will a household living in the edge of the city spend of commuting? That means when the distance is 80, what is the commuting cost? And if you recall from the setting at the beginning, that is the cost per block was 0.01. So if you have to travel 80 blocks, that would be 80 times 0.01 equals to 0.80 units. We're talking about thousands, so that means $800. Okay, we solved it. Now they're going to complicate our lives a little bit. Let's suppose that the population grows to 255,000. Now let's repeat C, D, and E. In C, we're going to get the optimum size of the city in terms of blocks. In D, we're going to get the optimum size of the consumption bundle, called bread in this example. And in E, we find the rent function in equilibrium. So let's start with C. To determine what is the size of the city that we need, we use this equation that basically is the area of the circle. So how much area do we need to fit 255,000 people inside? We solve for x, and we get that would be equal to 90. Okay, now we are going to solve D. D was about finding the size of C star. What is the consumption bundle that would get the rent function to be in equilibrium equal in the inside of the city as in the agricultural sector? So we know that outside of the city, the land rent is equal to 2. So we substitute. So it's 2. 2 is equal to 160 minus 0.1, and now we know that the x that we need is 90. So we substitute the 90 here, and now we just need to solve for C star. So solving for C star, we get that 2 is equal to 160 minus 9 minus 10 C star. And then we add C star on both sides, and we get 10 C star is equal to 160 minus 9 minus 2. That's 149. So C star is equal to 14.9. And now that we have the size of the consumption bundle, now we are going to get the rent function. We use again our rent function here, and we know that that must be equal to R equal 160 minus 0.1 times x minus 10 times 14.9. So that is 160 minus 149 minus 0.1x. And that will simplify to r equals 11 minus 0.1x. This is our new equilibrium. As you can see, instead of being here, now we're here. We end at 1110, 0, and here we have an origin to the 11. However, let's go and check the commuting cost. The commuting cost, of course, is t times x. In this case, x is 90. So 0.01 times 90 is equal to 0.9. The commuting cost, instead of being 800, now it's 900. This cost enters negatively in the utility function. Given that the population grows, we can infer that the utility of the people now it's a little bit smaller because the cost of commuting is a little bit higher. And this is just a calculation for the furthest house. But similarly, all the other households that have a positive distance from the center will have a higher commuting cost when the population grows.